Hey everybody, this is Nick Christian with Electronics. We're here again in the Miami Lakes Learning Center, and today we're going to be looking at CAN data links and how to troubleshoot them. So when we talk about CAN, the data link itself, there's two main layers that we want to concentrate on: the physical layer and the data link layer. The physical layer, the most of the time when we have issues out in the field, it's going to be related to the physical layer. So the physical layer refers to things like your wiring, your twisted pair, your terminating resistors, and the actual hardware chips that are inside each ECM or panel, which we would call a node. Anything that communicates on the CAN network is considered a node. So those components of the physical layer, if we kind of draw those out here, we've got an example here of a pretty basic multiple CAN data link setup here. So you can see we've got an after treatment ECM, we have an engine ECM, and then we have a DC, a dosing control unit. So those are three ECMs that would be on this. This is an example of a Tier 4 engine. We also have up here two NOx sensors that are also wired into the data link. So what we notice here is that we would have 5 nodes on this link, right? 3 ECMs and 2 sensors. Anything that either transmits or receives data over the data link is considered a node. So we have 5 nodes on the physical link here. We also have all of our wiring, which we can see. Now in this example, we can see we have a CAN A, a CAN B, and a CAN C network on here. This is very common in a lot of modern engines where we're gonna have more than one CAN network. Okay. One of these networks is considered a global network. The others are all gonna be considered local networks. The global network is going to be the one that is wired into our service tool connector here. Now the global network is the network that needs to have all of the available information on it. So the idea here is that if we have any COM adapter, whether it's a CAT COM adapter or any other third-party software, that they should be able to hook up over the global network and get certain required information off of that network. So we looked at the global network, and we know that it's the one that is wired into our service tool connector, and it has certain information that is non-proprietary information that can be read by any third-party software. We also have in this example here 2 local networks. So the CAN B and CAN C, in this example, we can see here now the after treatment ECM and the dosing control unit and the 2 NOx sensors here are actually wired into the CAN C network. And then we also have on the CAN B network the after treatment and the engine ECM. They have their own network that are wired together so they can share information without having to worry about messaging priorities or anything like that. And then back to the CAN C network here, the after treatment dosing control unit and the NOx sensor, those are all elements of the after treatment system on this engine. So the after treatment system has its own network also. So what we have here is 3 networks that we can share information on. The reason it's important to understand that we have these multiple CAN networks is that when we have a data link error message, generally -9 codes are pretty popular out there. The SPN that's attached to that -9 code is going to tell us whether it's the CAN A, B, or C, or sometimes it'll be called out as J1939 number 1, 2, or 3 network. It's important to understand that we have those multiple networks and that we understand which one of those networks that the fault is on so that we are troubleshooting the correct circuit. In this example here, if we get a -9 code on the J1939 number 2 network, well, we need to make sure that we're troubleshooting the correct wires. Otherwise, we're going to be sending the troubleshooting to the wrong highway here. The way I like to think about it is we've got 3 highways here, you know, highway A, highway B, highway C. Well, if an accident gets reported on highway B and we send the ambulance to highway A, that's not going to do any good for fixing the problem, cleaning up the mess where the accident was on highway B. So we need to make sure that we understand how many networks there are, and that when we do have a data link related fault, that it's going to be called out on a specific network. All right, so we're talking about the physical layer here. We've looked at the 5 different nodes that we have in this example here. We've looked at the wiring, how we have 3 separate networks here. Another aspect of the physical layer are our terminating resistors. These are required on our CAN data link networks. So if we go back to our example here, you'll see we've got the terminating resistors. Now they're 120 ohms each, and what you'll notice is each network, CAN A, CAN B, and CAN C, each network will have 2 of these 120 ohm terminating resistors. The placement of these resistors is important also. They need to be placed at the furthest point out on the CAN bus. Even say the CAN C network, where it has 4 nodes, the after treatment ECM, the DCU, and the 2 NOx sensors, 4 nodes, but still only 2 terminating resistors. So that's very important to remember, is that it doesn't matter how many ECMs or panels or nodes we have on a network. What's important is that we have 2 of those 120 ohm terminating resistors in each network, okay? Now, these are all parallel circuits, so when we go to measure for resistance, 2 120 ohm resistors wired in parallel, the resistance that we should see with the power off to the system is going to be around 60 ohms. When we're troubleshooting the physical layer on CAN networks, that's one of the things that we're going to look for, is measuring between the CAN plus and minus and see that we see 60 ohms with the power off to the network. All right, so let's look at checking for that resistance of our terminating resistors. We said the 220 ohms wired in parallel, we should see around 60 ohms of resistance. So right now I've got that here. I'm down on my service tool connector and I'm on my CAN plus and CAN negative, right? F and G on my service tool connector there. And if we see measuring resistance right now, we said we should see 60, but we're seeing like K ohms, 130, 200, like K ohms of resistance here, and it's bouncing all over the place. That is not what we expected at all. Well, the way that we're measuring right now, we forgot one very important step. We still have the power to the system on. When you see crazy numbers like this or really high resistances on your CAN network, sometimes some people may think that there's an issue going on there, or that that's an open circuit condition. What it really means, and most likely, is that you've forgotten to turn the power off. So we always check resistance with the power off. So I'm gonna go turn our power off. You watch the meter here. And when we turn the power off, we remove the power from our system, and there we go. There's around our 60 ohms that we would expect to see on a good CAN network if both of our terminating resistors are intact. So by this one little test here, we've checked that yes, our terminating resistors are intact, and our wiring, at least to the service tool connector here at this point, is also intact. All right, so we looked at resistance on a CAN network. So let's talk a little bit about the CAN network from the perspective of voltage, okay? We're gonna go out and look at the signal on an oscilloscope of the CAN signal, both the CAN plus and the CAN minus. But before we do that, I want to give you a little bit of an idea of what to expect when we see that, which also gives us an idea of what's happening voltage-wise. So if we look here, I've got an example of what's happening with a pretty typical CAN signal here. Now we know we have 2 wires. We have a CAN plus and a CAN minus. We can see this here, the green being our CAN plus, the blue being our CAN minus. Now, under circumstances where there's no data going across the data link at all, like an idle bus situation, both of those voltages on the CAN plus and CAN minus would be right around 2.5 volts here, right? So they're both the same voltage at that point, right? CAN plus 2.5, CAN negative 2.5. And that's gonna go on until it's time to send some data, right? So when the CAN plus, when it needs to send some data then, instead of being down here at 2.5 volts, the CAN chip internally is gonna take that CAN plus and it's gonna push it up to around 3.5 volts is a pretty typical voltage level. Now those voltage levels may be different, but the point is it's gonna take it from a 2.5 volt level and push it up to a higher level. The CAN negative, which was here at 2.5, the chip is gonna push that down to a lower level. In our example here, 1.5 volts, okay? And it's gonna do that for a certain amount of time based on what the ones and zeros are, right? So data link language, the binary bits that are going across, they're all ones and zeros, right? And how it determines how the internal CAN chip is gonna read these ones and zeros, right, is going to depend on the differential voltage between the CAN plus and the CAN minus. Now, here at this state here, when both the CAN plus and minus are at 2.5 volts, the differential voltage between those two, since they're both 2.5, the differential would be 0 volts. In that case, the chip is going to read that as a bit 1, okay? And then as we go along here, it's going to take a sample or a reading every 4 microseconds is the bit rate for a CAN network. So it's very, very fast. Every 4 microseconds, it's going to take a reading and determine the differential voltage. So these first 3 bits here are all 1 because the differential voltage has been 0 that whole time. Now, once we start to send some data, and instead of sending 1s, we need to send a 0 as part of our information, right? It's going to take that CAN plus and push it high, take the CAN negative and push it low. Now the differential, when it takes the sample right here, the differential voltage in this example is 2 volts. So when the differential voltage is higher, right, then now it's going to call that a bit 0. Okay? 4 microseconds later, it takes another sample. But what's happened? That voltage, when the CAN plus was high, the CAN negative was low, now they've both gone back to that 2.5 volt level. So the differential voltage at this sample is 0, so it calls that a bit 1. 4 microseconds later, it takes another sample. Now the voltage levels have gone high and low again, so our differential voltage here again is 2, and it calls that a bit 0. That's what that chip is doing all day long, is it's sending those CAN voltages either high or low, measuring the differential voltage between them, and based on that, determining 1s and 0s. It then takes that sequence of 1s and 0s and it turns that binary language into digital information. So now that we've looked at what voltage is doing in a CAN network, I want to point out one other thing here also. When we're measuring voltage with a multimeter out on the engine or on our piece of equipment, keep in mind that this is all happening extremely fast, right? Every 4 microseconds, it's switching between 2.5 and then that higher or lower voltage and taking a sample. Your typical digital multimeter will only sample at about 250 milliseconds or 4 samples per second. So what you're going to see for voltage with your regular digital multimeter is just an average of lots and lots of these bits that are going across because it's so fast. So what we can tell you from a voltage perspective is that the CAN plus should always be more than 2.5 volts, right? Because if it were always 2.5 volts, which means we'd always be sending 1s or an idle bus situation, the CAN plus would be 2.5 volts all the time. But we know that's never going to be the case. We're always sending data back and forth. So if this is part of the time at 2.5 volts and part of the time up at, say, 3.5 volts, the average voltage for that your meter can read is going to be somewhere above 2.5 volts, right? That's the best that we can tell you. For the CAN negative, again, idle voltage is going to be at 2.5 volts, and then it gets driven down to a lower level, to 1.5 volts in this example. So the voltage on CAN negative is always going to be an average of less than 2.5 volts. So CAN plus more than 2.5, CAN negative less than 2.5. That's what we should expect to see on the CAN with reference to ground for the CAN positive and CAN negative when we go to measure with a multimeter. So let's look at measuring our voltage out here on the engine. So I'm down at my service tool connector, right, and I'm measuring on pin G, that is my CAN positive, and pin B, which is my ground. And what do we see up here for voltage? I see 2.6 volts. That is above 2.5 volts. That's what we said that the CAN positive should read as somewhere an average of above 2.5 volts. So we're seeing that here. We're seeing the voltage that we would expect to see. Now if I change this and I go from G, which is the CAN positive, up to F, which is the CAN negative, right, and we go back to the meter here, now we're seeing about 2.4 volts, right? Less than 2.5 volts. So that's what we stated in the classroom there, that the CAN negative, the average voltage will be less than 2.5 volts. The CAN positive, the average voltage will be more than 2.5 volts. And then to understand what the chip is doing is it's constantly reading the differential between those two voltages and then determining the bit levels, either 1 or 0, taking all those 1s and 0s and then translating that into data. All right, so let's take a little deeper dive into looking at this CAN signal here. So we've got an oscilloscope set up here. Now, what we can see here is that I've got a signal captured, and channel A, the red channel here, that is our CAN positive. So what you can see happening here is that it's humming around here at around 2.5 volts, and then it gets pushed up to that level, much like what we saw in the classroom there, for so many microseconds. Now, right now we're at a 10 microseconds per division right now. So each box that you see here in the background on the grid is 10 microseconds. So the width of this signal right here when these two separate is about 4 microseconds, which is what we said the bit rate was on CAN. So to me, this is gonna represent, since those two voltage levels are far apart right there, the differential is around 2 volts, the way the chip is gonna read that, it's gonna read that as a zero, a bit zero. And then when the two voltages then go back together down here to the same level at 2.5, the differential then is gonna be around 0 volts. And so the chip is gonna read that as a bit 1. So the way we would read this is, this is 4 microseconds here, that would be a 0. This gap here where they're both back together again is about 8 microseconds wide, so that would be 2 ones, right? It's 2 samples. It takes a sample every 4 microseconds. This window is about 8 microseconds long, so that would be 2 bits where the differential is 0, so it would read that as 2 ones. So it would read this as 0, 1, 1, and then the differential here in this box is also high again, so this would be like 0, 1, 1, 0, 0, 0, and then they go back together, so 1, 1, 1. Hey, we're talking binary language here. We'll leave a lot of that to the ECMs, but I do think it's interesting to look at this and kind of know how the ECM and how the data link chips are determining what the data is. Again, it's all binary, ones and zeros. How does it determine the ones and zeros? By the differential voltage between the CAN plus and the CAN minus. It's just doing it really, really fast and looking at that information, parsing it all out, and turning it into data. All right, so since we've got the oscilloscope hooked up and we see a good signal going on here, let's take a look at some of the different fault conditions and what's gonna happen. So, we're lucky enough, I've got a couple of different ports here for our global network. That's the one that we're hooked up to looking at right now. So I've got B here, and what I'm gonna do is take B, which is ground, right? We're gonna go ahead and let's just see what happens if we take the CAN plus, and we're just gonna ground it out. And you can see our signal really looking bad here, and holy cow, we've got all kinds of alarms going off. Let's see what the panels are telling us here. Yeah, we've got J1939 communication loss, data erratic. We've got another panel here giving us a J1939 communication loss. So we've lost communication. Everybody's going nuts here. You can see by shorting out just that CAN wire here how the signal's affected, and we're getting all these J1939 faults. So let's go ahead and fix our problem here. Let's make everybody happy again. So that was shorting out, and you can see our signal is back to, looking pretty normal. We'll pause it here for a second. We can see the boxes here, right, where the two voltages go together, where they separate apart. This all looks pretty good. And so we'll go ahead and run again. Now let's see what happens if we ground out our CAN negative, which is pin F. So we'll short it out. Now our signal looks a lot different here. We can see, if we pause this here, so our CAN negative is the blue. It's the one that's grounded, right? And then our CAN positive, it still looks pretty similar to what it did. And so if you think about this here, what's happening? The differential voltage between the two, when they're down here on the low end, the differential is still near 0. So that would be that bit 1 that we were talking about. When the red line, channel A, that's the CAN positive, it shoots up. The CAN negative, though, is grounded out. It stays low, but the differential voltage in this case here is still, around 2 volts. So in this case here, you notice you don't hear anything going off and beeping either. We've shorted out the CAN negative to ground, but yet everybody's still happy. Everybody's still communicating. Our signal doesn't look like what we expect it to, right? So this may or may not cause some problems in the future for us if we have the CAN negative shorted to ground. It's definitely not what we want, but when you hear where CAN is a very, very robust system and it can tolerate a lot of different faults and things like that, and noise, things like that, this is an example of that. Robust system to where the CAN negative shorted to ground, everybody's actually still communicating. So some examples, some faults like this, CAN holds up pretty well to it. All right, so the last problem we're gonna look at here is we shorted the can positive to ground, we shorted the can negative to ground. Let's see if we have a short between the two. So we're gonna short F and G together here on my service tool connector, and we'll see what happens to our signal. Oh, we gotta run the signal here. And we can see, since they're shorted together, they look like the same signal. So there is never a differential voltage here. So basically, the chip is just reading 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 all the time because there's no differential voltage between the two. And when the panels and everybody that's asking for information sees that, hey, it's just reading a bunch of ones, there's no data, then obviously nobody's happy up here. So these panels are all looking for information. They're not getting it from the ECM because we have our can shorted and no information going across. We're getting all kinds of alarms here. All right, everybody, that's a wrap here from the Miami Lakes Learning Center. Hope you enjoyed this video on CAN networks, looking at how the networks are designed, the different networks that we may have, the global versus local, multiple networks. We looked at resistance, we checked it with voltage. We also checked out what the signal looks like and how the chip is looking at those voltages and determining the information. So if you like this kind of stuff and you want to get even deeper into troubleshooting CAN networks, -2, -9, -14 codes that you may see out there in the field, you can always go out to our DPC network. That's this website right here. And once you get there, you can check this class out, our electronics troubleshooting ILT. That's a week-long class down here in Miami where we troubleshoot all those aspects. And then afterwards, you can go to this class, the Electronics Troubleshooting 2, where we dive deeper into troubleshooting data links of all different sorts. So I hope you've gotten a lot out of this. We hope to see you down here soon in Miami Lakes. And once again, always remember, when you're nice to the electrons, they're nice to you.